Okay, looking at another example here, I have an overall reaction, 2x plus y2 going to 2xy, and I'm being asked to propose a possible reaction mechanism for this, given the dependence on the concentration of x and the concentration of y2, illustrated in the chart here based on experimental data. Again, I'm looking first for any concentrations that should not appear in the rate law. So here, I can see that when I doubled the concentration of y2, the rate didn't change. So I would expect y2 it is not showing any relationship to concentration, or a concentration change isn't showing any change in the rate, not affecting the reaction rate. So this should not appear in the rate limiting step. Now, I'm going to look at the relationship between x and rate, and I'm going to focus on these two trials here where the amount of y stays the same. So here, my rate final divided by my rate initial is 0.6 divided by 0.15, or 4 times faster. The concentration of x final in comparison to the concentration of x initial is 0.4 divided by 0.2, or only a change of a factor of 2. So I doubled my concentration, and that led to my reaction rate getting quadrupled. How could that have happened? Well, if the relationship to x was such that x was squared, then when I put my 2 times into that square, it would have affected the reaction rate by a factor of 4. So what I conclude from this is that my rate depends on x squared. I have the same relationship going on in the first and fourth trial, so I don't need to do it mathematically to confirm. I know that I'm going to have x with a coefficient of 2 in my rate limiting step in whatever reaction mechanism I propose. So what could happen here? What if y2 broke down into 2 y's? Since y2 doesn't appear in our rate limiting step, this step would have to be fast. Then 2x's might find these 2 y's to produce 2xy. Here I have 2 x's, and so this reaction could be my slow step and could lead to this, where did I put it? This rate law. So that works, but this mechanism is very unlikely. It's unlikely because it would involve 4 particles colliding at the same time. That doesn't make a lot of sense if you imagine all these particles flying around in space. 4 of the exact particles you need hitting at the same spot at the same time doesn't make a lot of sense. So let's try and come up with a reaction mechanism that's a little bit better. Although, on something like test or something like that, this would be acceptable. What if, hold on, I'm just going to erase this, give myself somewhere to write. And this answer lacks a little bit of creativity. If you saw the last example that I did, I'm kind of cheating using the same thing twice. But what if I had 2x coming together to form x2? And then I have my x2 reacting with my y2 to form 2xy. If you wanted, maybe you make the mechanism a little more complicated. You say reacting to form x2y2, and then you could have your x2y2 splitting into 2xy. As long as these steps are fast, and then this one is slow, this is a reaction mechanism that makes a little bit more sense given our thing. We don't have a lot of particles colliding. Maybe X doesn't like to make X2, which is what could make it slow. Maybe this has a high activated complex or a high activation energy. But this is a reaction mechanism that makes a little bit more sense given this situation. Also, we'll notice that it creates a rate which is proportional to X squared because of the 2 coefficient on X and not dependent on Y in any way. So there's a possible reaction mechanism for this reaction. It's not necessarily the right one. This is a made-up example, but it at least fits the experimental data.